Good afternoon, and welcome to the last and, well, slightly late, but really last session of today. Well, what a day, what we have experienced. That many sessions in our cozy database-related corner, and we'll close also with no exception. It's about, again, aspects of database internal operations, and I'm absolutely glad to invite here on stage Daniil Zakhlystov from Nebius. Please welcome on stage. Right, and he will present on Greenplum physical backups, and the stage is yours. Thank you.
Hi everyone, my name is Daniil Zakhlystov, and I work as a software engineer at open source managed database department at Nebius. And today I want to talk about how our team was first in the world to implement physical backups of the Greenplum database engine with the help of our tool called WAL-G. And I would like to start from some dates. As you may know, today is 4th of July, and it's called like national holiday in the United States, Independence Day. But I would like to mention two other holidays. And first one is March 31st. It's called World Backup Day. Second one is October 10th, and it's called World Mental Health Day. And I think that experienced DBA already knew how these two days are connected between each other. Because actually, good backups are the key to good mental health. So today, our focus will be how we actually achieve mental health, good mental health, by implementing good backups. And what do we exactly mean by a good backup? Well, I personally will define three criteria. First, they should be reliable, second, low cost, and third, quick to restore. And what exactly does mean reliable backup? Well, at first, of course, it should be able to recover, like it's a top priority. And it should have a tool to verify that it's actually able to recover, so it should be verifiable. It should be also encrypted because we don't want others looking inside our backups data. It should be well covered by monitoring. It should be easy to install, operate, and use and configure. And it also should reduce the risk of some human operator error. So it should automate as much as possible some dangerous operations. What do we mean by low-cost backup? Well, this is mainly related to the backup creation part. And backup creation should be low profile as possible. So it should not affect any internal database related routines. It should not interfere with user defined load, and in other words, it should be like low effort to create. It should be as low profile as possible. Also, it should be efficient and occupy low space in cloud storage service. And it should be able, of course, to throttle its resources consumption. So we don't want our backups to compete actually with the database engine for resources when they're making a backup. So my ex-colleague from Yandex, Andrew Borodin, once told this phrase, and that's why I decided to include it in the presentation. You don't think about good backups, and you never knew about the perfect ones. So I guess that's basically describes all of the previous slides points. And last criteria, good backups should be quick to restore. And actually, this part is completely different from the creation phase because contrary to the creation phase, during the restore, we want to utilize as many resources as possible. We want to restore as quickly as possible. We want to utilize all of the available resources. And of course, we should be able to tolerate some temporary failures, because we don't want our 6-hour-long backup restoration to fail just because there is maybe 2 or 3 seconds cloud storage error or maintenance. OK, after we discussed what is a good backup, let's see what Greenplum proposes to us out of the box. And it actually proposed something. It's called gpbackup. It's a CLI tool. And the main characteristics of this backup tool is that it creates a logical backup. And most of the disadvantages that are coming are actually inherited from the entire nature of logical backup. So at first, it locks the DL. And it means that, for example, you cannot alter the structure of your tables during the backup creation. Well, it also doesn't leave us any chances of achieving point-in-time recovery. And even these 2 points, they are actually like stopping a lot of clients of using this gpbackup in production. So it also is not really extensible because it doesn't support many storage engines, only S3, BoostFS, as I know. And also, it's not, there is no flexible backup policies management available, unfortunately. So now I guess it's a time to these moments that we all enjoy in a big tech comparisons, because we need a reason to invent our own wheel again. So let's invent it. Because, and to do that, let's look what Greenplum actually is. Well, Greenplum is actually many Postgres instances. But it will be an error to say that it's just a bunch of Postgres instances. It's better represented by the next slide. It's many Postgres instances running together, in parallel. And there is a single coordinator that manages these segments. So it means that to create a backup for Greenplum, we just need to create a bunch of Postgres backups. And to do that, we actually unexpectedly have a great open source database disaster recovery tool that is written in Golang. And initially, it supported only Postgres, but today there are MySQL, SQL Server, Mongo, Redis supported. So, and we are working hard on expanding that list. So today, we are adding Greenplum. It's actually the very nature of WAL-G is that it's designed to be extensible. It supports many storages. It supports many compression and encryption codecs. And you can actually bolt in your own codec or storage engine relatively easily. It also have got resources throttling, parallelism, since it's written in Go, it's pretty natural. And there are also flexible backup policies available. OK, we've got a tool to backup Postgres. Let's go backup Greenplum. And let's start from the simple Postgres cluster topology. It's not HA, it's just some Postgres cluster. And as you can see, we have a primary and replica. And we tend to do database journals archiving from primary and backups from replica, just to lower the stress on the primary node. We do that to the object storage. And how actually Postgres physical backup works under the hood? Well, that's quite simple process. At the start of the backup, we call the Postgres function called pg_start_backup. And what it actually does under the hood, it does 3 things. At first, it creates a checkpoint. Well, to describe it like really on the fingers, it actually brings the database catalog files on the disk to a consistent state. Then it enables full page writes Well, basically, it's a protection from some of the pages, parts of the pages being residing in a file system level disk cache. So we have to enable that to avoid some torn pages. That's how they call it in Postgres, in the backup. And the last thing is we record backup start LSN and begin copying. We begin uploading the database catalog files to S3. And after we finished, we just call pgstop backup and record the backup stop LSN. Well, that's simple. That's all. You now got a Postgres physical backup. But to restore such backup, you need actually two things. You need the database catalog copy that we created on the previous stage, and you need a continuous sequence of database journals, starting from the backup start point up to the desired recovery point. And by combining these two things, you receive a restored Postgres cluster. Well, this talk is about Greenplum, so let's see how we can utilize that approach to create a Greenplum backup. So as you can see on the picture, there is a single coordinator. It's a sample Greenplum cluster topology. So there is a single coordinator instance and 4 segments. And actually, you can look at this topology just like on a 5 Postgres clusters that we've discussed previously. So the process of backing up such system will be the following. We will just repeat the process of backing up Postgres multiple times, but we will do that in parallel. So just as we've done on the previous stage, we just call pgstart backup, start copying files to S3, and when we are finished, we just call pgstop backup. That's easy. Well, the problem is that after we've done all these backups, what do we actually want to consider as a backup stop point? Because when we will be restoring, we need some moment in time when cluster was in a consistent state. So we need somehow synchronize all these segments and must at coordinator node. And actually, this wasn't possible in Greenplum 6, but there was an extension called gpbackup that was developed for Greenplum 7. And my ex-colleague, as I was mentioning before, Andrew Bordin, he actually backported that onto the actual Greenplum production branch, Greenplum 6. So now, thanks to this extension, we can utilize the function to create restore points. And restore points means that it's a cluster-wide consistent point that was created when there were no running to face commits, to face transactions in the entire cluster. OK, we've now got some tool to create a restore points. We've now got a mechanism to create a Greenplum backup. Great. We've got database catalog copies, and we've got the continuous sequence of database journals up until the created beforehand restore points. And by combining these two, just like in Postgres, we receive a restored cluster. Well, that was easy, basically. But the actual question is, how do we achieve point-in-time recovery? Because yes, we can restore on some single restore points, but unlike Postgres, there is no option to restore on some sample LSN or like timestamp. And to create some PITR, we just basically will use the following approach. So we'll, if our RPO, for example, is 15 minutes, we just create these restore points each 50 minutes. And when we are asked to restore on some moment in time, we'll pick the closest one that was created before that point. OK, so I guess that was easy. Well, we now have got Greenplum cluster backups. That's great. But we want to create good backups. So let's get back to our 3 criteria. So first part is reliability part. And here is how our Greenplum cluster backup is organized. So initially, we call a single command that's called WAL-G backup push from coordinator. What it actually does, it spawns a bunch of SSH sessions on each segment. And on each segment, it just runs a usual Postgres backup. So I think that's a simple approach. But what is the problem? The problem is that, unlike Postgres, well, Postgres actually too, but Greenplum clusters, they may require a couple of days to create a full backup because they can be huge in size. And since we are running in a cloud environment, it's not perfect. And there can be some interruptions, SSH sessions may be terminated, so we need some approach to combat that. So we simply switch to polling. So when we are starting our backup, we remember all the bits of segments backup process, and then we check them from time to time and see what is their current state. And after all the segment backups are finished, we consider that backup as successful. And contrary, if, for example, some segment backup has failed, we consider that as a failure, and we're able to gracefully terminate all the running backups and return to a starting point, for example. So leave no traces. Restoring is quite the same, so I will not focus on that. Use the same scheme with SSH. So now we can sleep a little bit better because we know that our backups can be created even if there are some disturbances in network. And well, now we're good to go? I guess no, because we have part 2, low-cost backups. And let's now look at how Postgres backup is organized in the cloud storage. So as you can see, each backup holds its own collection of tar files. And these backup files are not connected between each other. There is no single backup that share any data with different one. And surprise, Greenplum segment backup is actually the same because we just borrowed the entire procedure. But here comes the problem. Since Greenplum is meant to store a lot of data, total backup sizes are unacceptable. For example, if you've got 100 terabytes cluster, you might not be willing to pay for 700 terabytes S3 cloud quota usage. So that's why we are interested in reducing this size. So one approach that we can use is called data duplication, and we might use the fact that, unlike Postgres, a vast majority of the data in Greenplum is actually cold data that's being written really frequently and being only read. So we can use that and store this vast majority of common data and share it between different backups. So that's a simple solution. So when we're making a backup, we just check, is it an append optimized table file or not? And if it is, it will go to a common storage. If it's not, it will go to a single backup storage. And here's how Greenplum backup layout of version 2 looks like. As you can see, there are 2 backups that are actually sharing some of the data. Oh, 1 second. And well, I guess that's good, but let's see how much. For example, on this picture, there is a comparison between different schemes. First one, V1, is initial, and second one, V2, is with the duplication. So as you can see, it's more or less the average number, but we mainly noticed at least 50% increase in cloud quota storage usage, like decrease. And now we are fine, I guess. We occupy not really much space, and we have fault tolerance for network. Well, we can do better than that, and we can actually see some cases when the duplication is not enough, because this append-optimized segment in common storage, it can be, for example, 1 gigabyte of size. And if you write even like 10 kilobytes to the tail of that file, you will have to re-upload the entire append-optimized table file again to the storage. So it's not efficient because you just store 2 copies of data that the only difference is that tiny tail. And to create incremental backups, we might come to a solution that is borrowed from Postgres, because we got increments in WAL-G for Postgres, and it works for heap tables. But since Greenplum also uses its own database table storage engine, it's called append-optimized, we need to invent something else. So we might look at the very nature of that files, and actually the noticeable difference is unlike Postgres, append-optimized files are being written only to the tail. So when we are creating a delta backup, we just can reference this previously written backup and upload only the tiny, tiny tail to our cloud storage. And we can reuse this approach for subsequent delta backups. OK, now we don't have to store these 2 huge segments. We can just create some deltas. And how much do we save? Well, it actually depends on your retention period, on how much you want to, how frequently you want to upload the entire data, just in case for maybe you want to re-upload the entire data only 1 month. So you want to save only 30 days of in your retention. But for most of our clients, it's just it's at least 65% economy in S3 cloud quota storage usage. So we've got 3 nice fancy features. Are we good to go? Well, we've got the last part, and it's called quick to restore. And well, it's actually, I'm not trying to compare our tool with gpbackup, because it's just different backup system. Because in our physical backups, it takes 8 hours to restore 80 terabytes cluster. I don't know how many days will require such restoration in gpbackup, but it will be much, much higher number than 8 hours. And what actually we have left to do? Resource totaling is still per segment. Ideally, it should be per host, because if you've got some disbalanced Greenplum cluster, you might have some tiny, tiny one segment and some really, really huge one, the second one. And resource totaling will not take that into account. And also important feature is that we might want to create, we might want to restore only single database or table, because if your backup is maybe 80 terabytes of size, and you want to restore only table that is like 100 megabytes of size, you don't want to download this entire backup. And good news, actually, it is done maybe like 2 weeks ago. So we are actively improving, and we strive to create like the best backups for Greenplum. And there is also some bonus part, because if you run backups of your Greenplum cluster with WAL-G, you can actually use this common append-optimized segment storage, not only for backup purposes, but Greenplum itself can use this append-optimized common storage in S3, because you can actually offload this cold data from your database hosts, and only download it from S3 only when there is actual need of reading it. So it's quite similar to Snowflake. Of course, there were some issues. Of course, we've encountered some strange errors from Greenplum. We fixed some strange bugs. Initially, they didn't support physical backups at all. So they said to us, well, there are no guarantees. We are not committing for that. And of course, there were some bugs. But good news, we fixed all of the bugs. We added tests to upstream Greenplum. And the really good news is that after we released our Greenplum physical backups with WAL-G, Pivotal actually committed that they now officially support these physical backups. And on top of that, recently they released their own physical backup tool. I'm not going to compare these tools in details. Well, it obviously has less features, but it's a great news that Pivotal actually officially supports that way. So it won't break in the future. And let's switch now to the funny part, how to use WAL-G and how to restore your first backup with WAL-G. And you can do that in only 3 simple steps. You can just configure WAL archiving. That's it. You can just create backup and restore from it. But to restore from backup, you need a special restore configuration file that describes the desirable cluster configuration. So you can specify where you would like to put each segment, which data directory, which port, which host. And after you've created such file, you just call WAL-G backup fetch latest, and hooray, you now received a restored cluster. It's that simple. OK, and we develop and maintain WAL-G in a GitHub repository. It's located by this link. And to be able to do a physical backups of Greenplum, you need 2 requirements. WAL-G should be at least 2.01 or higher version, and Greenplum 692 or higher. So that's actually it. I was trying to be compact because you've got some technical difficulties on the start. So I would appreciate your questions, and I guess I'll be grateful to see some of you at after party. Let's finally make this over.
Well, thank you so much for stealing part of my job. All right, so a round of applause. Thank you. Well, you just stole part of my official job, so to say, but that means I have less things to say. Now, the part remaining for you is questions. So, yes, I see a hand over there in the center. Please.
Hi. How do you achieve consistency between those segments? I'm not fully aware of the architecture, I must say, but like if you have a coordinator and then those segments, how do you set the restore point, and how do you make sure that it's the same on all clusters, or does it matter, or on the backup, or does it matter?
Yeah, of course it's matter. It does matter, and we use a special extension. It's called gpbackup, and the main responsibility of that extension is to create such restore points. They are being created from the coordinator segment, and actually what it does under the hood, it waits until there are no two-phase commits running in the system, and it forbids any new two-phase commits until this restore point will be created. So that's how it's being managed from coordinator. After this moments actually appears, we just write usual Postgres restore points to the same to each segment, and it's being written to the WAL itself. And when we restore the backup, each segment replaces that WAL until that point, and then stops. That's how we achieve that.
is there a failure point there? Like, can it fail if coordinated fail?
Can it fail? Well, we create these points each hour, and actually we didn't notice any frequent failures in production. So there were some fears that they might interfere with user-defined loads, but actually to create them, they are lightweight to create. So on practice, there are no conflicts, and clients are happy.
Thanks.
Excellent. Right. Any other questions? Yes. A hand, a few rows in front.
Thank you for your talk. And I also have a couple of questions about backup appliance scenario. So if I understand it correctly, these shards or
Segments.
Are independent, somehow independent. So
Yeah,
they have different data, run on different machines. And suppose some disaster happens on one segment and you have to apply a backup, but other segments and other data are safe. So do you anyway roll back to the latest checkpoint and lose all the data, even on the segments that were not corrupted, didn't suffer somehow?
Well, no, we just use these physical archives to rest up the file segment, and then it can replay the WAL up until the desired point, and it's also okay, because well, Greenplum won't commit any new changes if you have some failed segments. So the failed segment will just restore from backup, replay all the WALs if they have been archived correctly, and this will basically make sure that it's in sync.
So it tries to restore the failed segment to actually the last point, not to the checkpoint, but
not to the restore point, but just up until the end of WAL.
Okay, and if the disaster is such severe that you lose your write-ahead log?
Yeah, then you are in trouble and you have to restore the entire cluster up to the restore point, because there is no redo in Postgres or Greenplum whatsoever. So yeah, then you are out of luck, unfortunately.
Yeah, and a little bit the next question. So suppose you lose your write-ahead log on one segment, so you're not actually able to restore to even a checkpoint, because if I understand it properly, a checkpoint still uses a part of a write-ahead log after the backup. So how do you actually restore your cluster if some segment doesn't have write-ahead logs, the whole data burned in the fire and...
Actually...
Right, I'll just interrupt. Can you answer that in 7 seconds that you have remaining?
Okay. Actually, it is the same problem that Postgres has. If you have a backup and you want to restore on some points, you're obliged to have all these WALs in your cloud storage to restore correctly. So it's the same.
Right, and please continue with this. We really are running out of time, so this is an excellent opportunity to continue that discussion in the hallway and before the reception, the social event. Right, so the last task for you remaining, who gets the prize?
Well, I guess the last person was really intrusive, and I mean, like, he asked really interesting questions. And
so the gentleman in the third row, all right?
Thank you.
If you could raise your hand just for yes, over there. Right. So with this, a round of applause, and this is the end of the last session, right? So thank you, Daniil, for presenting this. Now, announcement. We will have the official closing of this conference in Hall 1. That's across the lobby on the other side. And that is going to happen in like 5 minutes. So if you are interested, certainly please, well, it's not that you're interested, you must be interested in that. Right, so the official closing ceremony will be there. And then afterwards we have a social event, a reception, and a free time for interaction and networking. discussions, all of the follow-up questions that you didn't have an opportunity to ask for speakers, and just, well, mingling with your fellow colleagues. Thank you so much.